Hello, thank you for joining me once again on the Basic Academy. On today's video tutorial, I shall be showing you how to analyze LIKERT-SCALE data regression analysis using Excel and SPSS. Essentially, how to analyze LIKERT-SCALE data regression analysis using Excel and SPSS. Okay, supposing we have this particular LIKERT-SCALE questionnaire here to be used for this analysis. Here we have the variables, which includes innovativeness, INV, risk-taking, RT, SME's growth, SG. And look at the codes for each of these particular variables here. INV 1 to 5 for innovativeness, RT 1 to 5 for risk-taking, SG 1 to 5 for SME's growth. And look at the items captured under each of the codes, as you can see here. Now, the agreement scale here is strongly disagree 1, disagree 2, undecided 3, agree 4, strongly agree 5, as written here, as you can see here, captured here neatly. Now, let's assume that this is the model we want to estimate here. The dependent variable here is SG, which is SME's growth, and the two independent variables here are innovativeness, which is INV, and risk-taking, as you can see. Now, if the data we shall be using here is normally distributed, haven't carried out normality test, we are going to employ linear regression and Pearson correlation. However, if our LIKERT-SCALE data is not normally distributed, we shall be using ordinary regression and Spearman rank correlation, as you can see. Okay, so this is the questionnaire we shall be using for this particular illustration. Now, let's assume that this questionnaire has been distributed and look at the responses generated. And this questionnaire was distributed to 20 respondents, as you can see here. And look at the codes again for each of those particular variables captured. INV 1 to 5, RT 1 to 5, and SG 1 to 5, as you can see here. Now, what we're going to do is that we're going to transform these particular variables by taking the mean values of each of the variables, as you can see here. So for us to do that, we'll simply insert space after each set of a new variable, as you can see here. We'll insert space so that we can demarcate that of innovativeness from RT, which is risk-taking, and SG, as you can see here. All right. So what I'm going to do is that I'm going to transform the variable by taking the mean values of this. So for me to do that, I'll simply give it a new name, which is INV. Remember, the INV stands for innovativeness, as you can see, INV here. So I'm going to take the mean values of all of these to create a new one, INV. Okay. All right. For me to do that, I'll simply press equals to, type in equals to here, then open a bracket, then add these variables. The codes given to them have C3, which is C3 here, 2 here is have been added, as you can see. Then you click the next variable, followed by plus sign. You click the next response, followed by plus sign. Click the next response, followed by plus sign. And the last one, then you close. Then divided by 5. Why are we using 5? Because we have 5 codes here for this particular variable. IV 1, 2, 3, 4, 5. So that's why we're using 5 here. So this C3, D3, E3, F3, G3 simply represents C3, as you can see in Excel, D3, E3, F3, and G3. So the 5 of these particular codes here are representing a new variable which we shall be generating, which is INV. So having typed this, simply press enter on your keyboard. As you can see, it has generated the mean values of all these responses here for this particular respondent here, respondent number 1 here. So for us to calculate for the remaining ones, simply take your cursor to get this plus sign here, this tiny plus sign, as you can see here, then left click and hold and drag down. Okay, it has generated the mean values of all the respondents on this particular innovativeness variable here, as you can see. Okay, clicking down, looking up here, you can see it's changing. You can see that for each of the respondents. Okay, we generated a new variable from this particular 5 responses here, as you can see. These particular 5 variables here, we've generated a new one, transformed into a mean. For us to do for the next one, you simply type RT, okay, as you can see here, which is a new variable that we shall be creating from here. Then simply copy this formula here, okay, copy, then simply paste it here. So once you paste, it's going to create for its own variable here, as you can see. Now, here we have I3, J3, K3, L3, M3, which is for I3, which is RT1, I3, can you see that? J, 3, okay, K 3, and the L 3, then M3. Okay, as you can see, it has generated the mean values of RT1 to RT5, as you can see. Now, for us to get for the remaining ones, you simply keep your cursor here. Once this small plus sign shows here, left click, hold, and drag down. As you can see, it has calculated for the rest for only RT1 to RT5. Then for SG1 to SG5, repeat the same process. Simply copy, okay, then paste. Then above here, you simply type SG, okay, which is the new variable we want to generate or create. Okay, so this is the formula of copied and pasted, and it has created the mean value for SG1 to SG5, as you can see, OPQRS, which is what we have here, O3, P3, Q3, R3, S3, as you can see here. Okay, now for us to get for the remaining ones too, you keep your cursor. Once this small plus sign shows here, left click, hold down, okay, and drag down. It has created for SG. So we have our 3 new sets of variables here. We have INV, I'm going to differentiate with the color, followed by RT, as you can see, then SG. Okay, so these are the 3 variables we shall be using for this particular analysis. So these are the transformed variables from these particular ones here. As you can see, the mean values of all of this gave us this, the mean value of all of this gave us this, the mean value of all of this gave us this particular one. So we shall be moving these 3 new variables to our SPSS. So let's go to our SPSS page. On our SPSS page here, you simply go down to your variable view, you click variable view. Here you type INV under name, followed by RT, that is a new variable we created, then followed by SG. Okay, as you can see, we have INV, RT, SG. Now, if you click your data view, you see them displayed here, as you can see. All right. So what we are going to do is that we're going to copy the transform variables and paste transform data and paste them here. So simply go back to our Excel. For INV, look at the transform variable here. You copy, go to SPSS, and you paste. Okay. You go back to Excel. The transform for RT is this. You copy, you go to SPSS. You simply do what? You paste. For SG, you repeat the same process. You copy. Okay, you go to SPSS and you do what? And you paste. So we have our 3 new transform variables we shall be using for this particular analysis. So the next thing we need to do is for us to carry out a normality test on these variables to find out if they are normally distributed. Okay, for us to do that, simply click Analyze, Descriptive Statistics, select Explore. Okay, now these 3 variables, you highlight the 3 of them and move them under dependent list here. You click this arrow to move them under dependent list. You simply click Plots. Okay, you uncheck Stem and Leaf, then select Histogram, then select Normality Plots with Test. Okay, simply click Continue, then you click OK. Okay, wait for some few seconds, the result will appear. Yes, we'll have the result. We'll have case processing summary, we'll have descriptive statistics, then we'll have test of normality, which is what we are most interested in. However, if you want to see the interpretation of these 2 tables here, together with other information captured under, kindly go to the previous video I've made on how to conduct normality test. Okay, kindly watch the previous video I've made on how to conduct normality test to see the interpretation of all these tables here. However, for the purpose of this video, I shall be concentrating on this test of normality here. Okay, all right. Now, looking at this test of normality, we have 2 tests of normalities, which is Kolmogorov, Smirnov, and Shapiro-Wilk. So these are the 2 tests of normality. All right. Now, if your data set is above 100, you simply use Kolmogorov, Smirnov test. Okay. If your data set is less than 100, you use Shapiro-Wilk. In our own case, our data set here is 20, which is less than 100. So we shall be relying on Shapiro-Wilk because we have a small sample size, which is less than 100. Okay, as you can see. So because we have a sample size that is less than 100, we shall be relying on Shapiro-Wilk. Had it been it's more than 100, we would have used Kolmogorov, Smirnov. All right. Now, if you look at this particular SIG value, which is the p-value, you discover that they are all greater than 0.05, which shows that our variables here are normally distributed. that is the data generated for this variable here, are normally distributed because they are greater than 0.05, as you can see, using 5% level of significance. So the probability values here we have 0.129, 0.321, 0.184. They are all greater than 0.05, which shows that our data set here at 5% level of significance, they are normally distributed, okay, using Shapiro-Wilk, since our sample size is less than 100. Okay, now because of our data here are normally distributed, we shall be relying on the linear regression and Pearson correlation. Remember what we stated earlier on here, we say that if our data set here are normally distributed, we'll use linear regression and Pearson correlation. However, I've also made another video previously on how to carry out ordinary regression and Spearman rank correlation of normality of LIKERT-SCALE data. You can also watch the video I've made around this. Okay, but in this particular video here, our data is normally distributed, so we shall be using linear regression and Pearson correlation. You can watch my previous video on how to analyze ordinary regression and Spearman rank correlation using LIKERT-SCALE data. Okay, so now let's go back to our SPSS page. Now, since our data set here is normally distributed, we shall be conducting linear regression. All right, for us to do that, simply click Analyze. Okay, then scroll down to Regression, then select Linear. Okay, linear regression. The dependent variable here is SG, so we move it under dependent list. The two independent variables here are INV and RT. You highlight the two of them and move them under independent box here. Okay, then you simply go to statistics. All right, you select W-Watson, then select collinearity diagnostics. Okay, these are the few ones I'll be using here. Click continue, then simply click OK. Now once you click OK, your result appears, as you can see here. Now the first result that appears here will have model summary. The second table here will have model summary that captures the R square, adjusted R square, standard error of the estimate, and W-Watson. The R here represents the Pearson correlation. The R here represents the R square, which is a test for goodness of fit. We'll have the adjusted R squared. Now for the interpretation of this particular table, I'll move to our PowerPoint where I've moved it already for easy interpretation and explanation. Okay, let's go to our PowerPoint to see how this is interpreted. Okay. Now moving down to our PowerPoint here, remember we'll have the model summary table. The first variable there is R, or the first indicator there is R. This is the Pearson correlation coefficient, which describes the strength and direction of linear relationship between two or more variables. The R value of 0.586. Remember, the R value there is 0.586. You can cross-check that. You can see 0.586, as you can see here. Okay, let's go back to the PowerPoint. Shows that there is a strong and positive correlation among the three variables. Why did we say they are strong and positive? This is greater than 50%, as you can see, it's 50% and above. And also, there is a positive sign here, which shows that there is a strong and positive correlation among the three variables of interest. Now, the next is the R squared. The coefficient determination, which is the R squared, is used to measure the goodness of fit or the explanatory power of a model. Technically, the R squared gives the proportion or percentage of the total variation in the dependent variable that is explained by the independent variables. Okay. All right. Now, the R squared value of 0.344, let's look at it. The R squared value here is 0.344, as you can see. Okay. Now, the R squared value of 0.344 shows that about 34.4% changes in SG, which is SME's growth, is explained by INV and RT jointly, while a greater part of 65.6% is captured by the error term. This shows that the model has a poor fit. It has a poor fit because this is less than 50%, okay, which is at 4.4. It shows that the model has a poor fit. Remember, if you look at the result we generated here is 0.344, which is at 4.4, which shows that the model has a poor fit because this is less than 50%, okay. Now, we have the adjusted R squared. This is the modified version of R squared that has been adjusted for the number of independent variables in the model. The adjusted R squared penalizes the R squared for the addition of variables which do not contribute to the explanatory power of the model. The adjusted R squared value of 0.267 shows that about 26.7% changes in SG, which is sales growth, is explained by innovativeness, which is INV, and risk-taking, RT, jointly, while a greater part of about 73.3% is captured by the error term. It also shows that the model has a profit. Okay, remember this is the adjusted R-square value, which is 0.267. We can also cross-check that here. We have it here, 0.267, which is the adjusted R-squared. Okay. Now the next is the W-Watson statistic. The W-Watson statistic measures the evidence of autocorrelation in the residuals. The acceptable W-Watson range of no autocorrelation is between 1.45 and 2.44. Thus, the fitted regression line results show that there is no evidence of autocorrelation as indicated by the W-Watson statistic value of 1.77. Okay, let's also cross-check. The Watson value here is 1.77, which shows our model is not autocorrelated, as you can see here. Alright, so that means our regression line does not have evidence of autocorrelation, as you can see, 1.77. The next is the ANOVA. The ANOVA or F statistic measures the overall significance of the model. It consists of calculations that provide information about levels of variability within a regression model and form a basis for test of significance. Okay, we can look at our ANOVA result. Okay, scrolling down a little. This is the ANOVA result table here. Look at the F statistic value here, which is 4.452, and the probability value here is 0.028, as you can see here. Okay, now the result confirms that the overall regression model is significant for the data, and this was captured by the ANOVA F statistic value of 4.452 and its associated probability value of 0.028 that was found to be significant at 5%. Now, if you look at this probability value here, it's less than 0.05. Of course, using 5% level of significance, this shows that overall significance of this model is good. All right, as you can see here, because the ANOVA measures the overall significance of the model. As you can see, look at the ANOVA F statistic value here, which is 4.452. You can cross-check that again from your ANOVA table, 4.452, and a significant value of, or probability value of 0.028, as you can see here. Okay, because this is less than 0.05, it shows that the overall significance of this model is good. Okay. Now we have the part captured as coefficients. Okay, let's go back to the SPSS page here. We have coefficients. We have the unstandardized coefficients, as you can see the values here, the coefficients values here. Look at the variables INV and RT. They will have the T values. Look at the respective T values. We'll have the probability values. They will have collinearity statistics, which includes the tolerance and VIF. Okay, so remember this particular interpretation has also been moved by PowerPoint. Okay, let's go back to the PowerPoint. Regression coefficient. The column labeled unstandardized coefficient depicts the estimated coefficient. The coefficient shows the sign and size or magnitude of change. They are computed by the standard OLS, which is ordinary least square formula. We also have the standard errors under the coefficient. The standard error column reports the estimated standard errors of the coefficient estimate. It measures the statistical reliability of the coefficient estimate. We also have the T statistic, which is the T value. The C statistic or the T value, which is computed as the ratio of an estimated coefficient to its standard error, is employed to test the statistical significance of individual regression coefficient. To interpret the T statistic, you should examine the probability value or p-value captured as SIG. Given a p-value, you can tell at a glance if you are to reject or accept the null hypothesis. Now, if you go to the results, you discover that the INV coefficient value, which was found to be 0.231, as you can see from the unstandardized coefficient, you can go back to SPSS to see that 0.231, as you can see for INV, under the unstandardized coefficient, as you can see here, shows that a unit increase in INV on the average increased sales growth, which is SG, by 0.31 units. As you can see, going by this value here, it shows that there is a direct relationship between INV and SG, because there's a positive sign here. And it further shows that a unit increase in IMV on the average increased SG by 0.231 units. The RT coefficient value, which was found to be minus 0.119, shows that a unit increase in RT on the average decreased SG, which is sales growth, by 0.119 units. As you can see, if you go back to the SPSS page here, the coefficient value of RT here is minus 0.119. As you can see, that means there is an inverse relationship between RT and SG. As you can see, there is an inverse relationship between RT and SG. Okay? And that's the reason why we say that it shows that a unit increase in RT on the average decreased SG by 0.119. Why do we say decrease? Because there is a negative sign here, as you can see. The next is the T statistics and p-value, which is the SIG. The p-value represents the SIG. For INV, the calculated t-value for the relationship between INV and SG is given to be 2.937. 2.937, let's confirm it. As you can see here, the t-value for INV is 2.937, as you can see here. Okay. With an associated p-value of 0.009, that is, the t-value for INV is 2.937, and the p-value, which is the significant value, is 0.009. As you can see from the 0.009 from SPSS, as you can see here, 2.937 and 0.009 as captured here. Okay. Since the p-value is less than 0.05 at 5% level of significance, we conclude that INV has a positive and significant impact on SG. Why do we say positive? Because there's a positive sign here, okay, which shows that's a direct relationship. Okay. And why do we say it is significant? Because the probability value here is less than 0.05, of course, using 5% level of significance. For RT, the calculated t-value for the relationship between RT and SG was found to be minus 1.105, with an associated p-value of 0.266. Let us confirm that also. For RT, the t-value is minus 1.150, and the p-value of 0.266, as you can see here, 0.266 as captured here. That is for RT. Okay, let's go back again. We say the calculated t-value for the relationship between RT and SG was found to be minus 1.105, with an associated p-value of 0.266. Since the p-value is greater than 0.05 at 5% level of significance, we conclude that RT has a negative and insignificant impact on SG. Why do we say negative? Because there is a negative sign here. And why does it have an insignificant impact? Because the p-value here is greater than 0.05. And that's why we say it has an insignificant impact on SG. Okay. Now we have the collinearity diagnostics. The two values given are tolerance and variance inflation factor, VIF. The tolerance is an indicator of how much of the variability of the specified independent is not explained by the other independent variables in the model. What it means here is that the tolerance is an indicator of how much of the variability of the specified dependent variable is not explained by other independent variables in the model. If this value is very small, that is less than 0.10, it indicates that the multiple correlation with other variables is high, suggesting the possibility of multicollinearity. For VIF, the VIF is just the inverse of the tolerance value, that is 1 divided by the tolerance value. VIF values above 10 would be a concern here, indicating multicollinearity. The commonly used cutoff points for determining the presence of multicollinearity is a tolerance value of less than 0.10 or VIF value of above 10. Okay, as you can see here. Now, the tolerance value for each independent variable is 0.953. We can also cross-check that. For tolerance value, look at the collinearity diagnostic. For tolerance value here, for each of these independent variable here is 0.953, as you can see here. 0.953, 0.953, okay, which is not less than 0.10. Therefore, we have not violated the multicollinearity assumption. This is also supported by the VIA value, which is 1.049, which is well below the cutoff point of 10, as you can see. So the VIA value here is 1.049, as explained. Let us cross-check that too. So as you can see, the VIA value here is 1.049, as you can see here, okay? And this particular VIA value here is well below the cutoff point of 10, which means here that our model here is free from multicollinearity. As you can see, that the regression model here is free from multicollinearity, okay? Now, this is essentially how to conduct a linear regression using LIKERT-SCALE. We can also show you how to conduct a descriptive analysis from this particular LIKERT-SCALE data. For you to do that, simply click Analyze to conduct descriptive statistics. Okay, go to Descriptive Statistics, click Descriptives. Okay, move all the variables under Variables box here, as you can see here. Simply click Options. Okay, you can select variance, kurtosis, skewness. Okay, click Continue. Then simply click OK. As you can see, this is a descriptive statistics result from that LIKERT-SCALE data. Okay, as you can see, that the transformed LIKERT-SCALE data. Look at the descriptive statistic result here. We have the minimum statistic. First of all, we have the end statistic here. There are number of variables included. We have the maximum, we have the mean, the standard deviation, the variance, the skewness, and the rest. We can also conduct correlation for this particular data. Simply click Analyze, then go to Correlate, select Bivariate. Okay, then move all your variables to under variable box here. Now, because our data here is normally distributed, so we'll return it on Pearson. Had it been is not normally distributed, we would have used Spearman, but because it's normally distributed, we'll return it on Pearson correlation. Then simply click OK. And once you click OK, you have your correlation matrix result here. As you can see, the correlation between INV and RT is found to be 0.217, which is poor, which shows that it's a poor correlation between INV and RT. And this particular correlation is also insignificant. As you can see here, the probability value here is greater than 0.05, which the value here is 0.358. So the correlation between INV and RT is poor, going by the value of 0.215, because less than 0.50, as you can see, and it's also insignificant. And the correlation between INV and SG is actually found to be strong and also statistically significant, as you can see here, because the correlation coefficient value here is 0.54, which shows that it's a strong correlation between INV and sales growth, which is SG, and it's also found to be statistically significant, as you can see. However, if you look at the correlation between RT and SG, it's found to be negative and poor, as you can see, minus 0.103, which shows that there is a negative and poor correlation between RT and SG, going by this value here. And it's also found to be statistically insignificant because the probability value here is greater than 0.05, as you can see. So RT has a negative and insignificant correlation with SG, as you can see here. So essentially, this is how to conduct a LIKERT-SCALE linear regression. First of all, you transform your data, as we have done here. After transforming them, you move them to SPSS to test for normality. And if it is found to be normally distributed, you use linear regression. If it's not, you use ordinal. I've made a video on how to use ordinal regression as explained earlier. Okay, but for those of this particular video, we actually use linear regression and Pearson correlation. Okay, if this is your first time of coming to our channel to watch our video, kindly click the subscribe button to get more video updates. All right, thank you for watching, and also thank you for listening.